Okay, let's get things underway. So welcome to the February meeting of the RASC Ottawa Centre. Special welcome to RASC members and visitors. And a special welcome as well to folks from other RASC centres who might be joining us here this evening. Couple of security things when it comes to Zoom. We are in webinar mode, which means that we cannot be Zoom bombed. However, some people may try to come in and post nefarious links in the either in the chat or in the question and answer window. So if there's any URLs in those two windows, please do not click on them. Okay, we have turned off raise your hand. If you have any questions for the speakers or for the panel here, please use the question and answer box. So here's what's on for tonight's program. Obviously the introduction, I'm going to go through Ottawa skies. Very pleased to have our guest speaker here this evening, David Rogers, who's going to be talking about space junk. We're going to have about a 5-minute break, M&M challenge. And Sharon Odell is going to be talking about the Dominion Observatory and in particular women scientists. We have a bunch of observations and then some announcements at the end. So let's move on then. Welcome to the new members. We have 10 new members so far in 2021. And welcome to the RASC Ottawa Centre. Members in the news. Well, Jim Thompson, one of our members here, has had one of his articles published in the Astronomy Technology Today publication. Congratulations there, Jim. And it's all about different filter comparisons. He's given us some amazing talks on those in the past. Okay, so let's take a look at the Ottawa skies for February. Next slide. Well, you'd be pleased to know that there's a bunch of comets up there. Most of them are pretty small, pretty faint, but we have Comet 141P, Mashalov 2, and this is where it is across the sky. Now, I realize these slides are flying past at quite a rate. Don't worry about it. Local members will have copies of these slides in the Astronotes. Those will be coming out shortly after the meeting. Okay, so next slide. We have another one, Comet 156P Russell Linear. And next slide. This is what it looks like. This is from January 9th, 2021, near the Pinwheel Galaxy. And you need a 10-inch or larger telescope to see this, and you'll be able to see it through mid-February. And if you miss it, 6.4 years from now, it'll be back. And the last one is 29P Schwarzmann-Walkman, evening sky, January to early March. And then it'll disappear for a while and be returning in the dawn skies in mid-July. In terms of the phases of the moon, so the full moon is on the 27th of February, and our new moon is on the 11th. And let me see. So the full moon for this month is known by the indigenous peoples as the snow moon because the heaviest snows usually fell during this time of the year. And it's also known as the hunger moon because it was difficult to get food because of the harsh weather conditions. Next slide. Days are obviously getting longer, as you can see from the rise and set times on the first and the end of the month. So yeah, we're definitely moving towards spring. Mercury is not visible. It's just way too close to the sun. There's no elongations eastern or western this month. Venus is not visible. It's rising and setting with the sun. This is a very poor month when it comes to planets. Mars is about the only one that's visible. It's high up in the sky in the evening. It's going to be visible all month. Jupiter's chasing the sun as well, as is Saturn. The next slide. Yeah, so that's not visible. And Uranus is visible all evening, and Neptune is visible in the early evening, just the first half of the month. And there's our cartoon of the month. Okay, so we're going to move on then and welcome our guests. Oh, yes, I forgot about this. One of the things that I do when I'm not chairing the meetings is that I do a lot of virtual outreach, particularly to scouts and guides. So if you know any folks in those areas, and well, I primarily do it in the Ottawa area. I have done it across Canada. So if you know of a scout group or a Girl Guide group that's interested in having a virtual astronomy session, the one for the Beavers and Sparks is 45 minutes long, and the other groups, it's about an hour and 15 minutes long. I deliver it using Zoom, and I'm taking bookings past March right now. Actually, February is pretty well fully booked. Last night I had 140 beavers. Their age is 5 to 7, and it's amazing some of the questions you get from kids of that age. And I've got on the 17th of the month, I'm doing one for a bunch of scout groups, and I think I have about 300 on that call. So anyways, if you are interested in that, just email me, meetingchair@ottawa.rasc.ca, and we'll try to pick some mutually convenient dates. And since I did the first program, I actually have a follow-up astronomy session for the older kids. And this one it says coming soon. It is here. I have completed it. And we go into a little bit more depth. We talk about the moon, the sun, where are we, exoplanets. We mess around with Messier, and I go into stellarium in a lot more detail. So that one is also available. Okay. So we're going to stop sharing here for a second. I'd like to introduce to you David Rogers, who's from Carleton University, and he's going to be giving us a talk about space junk. So welcome, David.
Thanks, Dave. Thank you to everyone for attending, and I hope you're interested to learn a little bit about space junk. I did a, oh, sorry, I'll just share my screen here so you guys can see the slides.
And David has no video, so in case you're wondering where his face is, he's not there, but he's certainly, audio is fine.
Okay, just making sure everyone can see. The slides are clear?
Yeah, the slides are good.
Cool. All right, so specifically, I did a master's thesis at Carleton University, and it relates to space junk in the sense that I was trying to figure out a way to capture debris in orbit, even if you don't know the mass of that piece of debris, and if there are forces disturbing you while you're trying to capture it, so external perturbations. And so the title of my thesis, Simple Adaptive Control for Spacecraft for Trajectory Tracking Involving Uncertain Masses and Perturbations. And so why should we care about space junk? By the year 2015, there was about 13,000 pieces of debris larger than 10 centimeters. There were two fairly major events that helped increase this. In 2007, there was actually a missile fired at a satellite that blew it into many pieces. And then in 2009, there was an unintentional collision between two satellites. And so those both caused quite a spike in the graph of debris in orbit. And if two pieces of debris collide in orbit, they produce many smaller pieces, and this is known as Kessler syndrome. It's a little bit analogous to a nuclear reaction in the sense that you get one collision producing more than two particles afterwards. So it's an increase exponentially. And so the European Space Agency estimates that if we want to at least keep the amount of debris in orbit stable, not even fix the problem, but just not make it worse, we probably have to remove about 5 to 10 large dead satellites per year. And that graphic there is just sort of a representation of the debris in orbit. And you can see there's quite a bit around the particular ring, and that's the geosynchronous orbits, because that's a very common place to put satellites. So there's a lot of defunct ones in the geosynchronous orbit. One thing that's definitely worth mentioning about bringing debris down and getting it to burn up in the atmosphere is that as many of you probably are aware, the ionosphere around the Earth actually changes in size according to the solar cycle. So when the sun's magnetic field flips every 11 years, it has quite a dramatic effect on our ionosphere, and then that has an effect on the drag that debris experiences at same given altitude. So I have a colleague at Carleton University, actually my undergraduate, who performed some experiments about if you have a satellite at a given altitude, depending on what part of the year, what year you're in, and what position in the sun's solar cycle you're in, how quickly will that debris come down? And you can see on the graph here with the yellow line, basically it has a fairly significant impact. And then there's also the question of what if we do nothing? So this is an example taken from a dead satellite, I believe that was launched by Canada, RADARSat-1. And it's at roughly 800 kilometers altitude. And you can see that if you were to just wait for atmospheric drag to bring RADARSat-1 down till it burns up, we'd be waiting until past the year 2500. So we're sending up more satellites faster than they would be coming down. There's a wide variety of capture methods that have been suggested. Some are more practical than others. Many talk about using a robotic arm to have a sort of cleanup satellite approach a piece of junk and grab it. There's different ways of doing this. There's also more exotic ideas like firing a net to capture something, or even capturing a large field of little pieces, even using a sticky net. I've seen some people talk about firing harpoons. I've seen people talk about using a charged capacitor to tack weld onto a dead satellite. There's all kinds of methods. But my research was primarily focused on, once the satellite has been captured, how do you control your movement if you don't necessarily know its mass and if you have perturbations trying to knock you off course? So it's somewhat independent of the capture method. It's after the capture has been completed. It's basically when you're towing the debris down, trying to get it to burn up in the atmosphere. So, okay, I've got a little video to show here from the European Space Agency. So my apologies, the videos weren't working in the slideshow, but they should play here. And as you can see here, it's just a simulation where it's showing an actual arm being used. So if you can everyone see the position of my cursor on the screen, or is my cursor hidden?
Your cursor's there.
Okay, good. So yeah, you can see that there's basically a cleanup satellite approaching this dead satellite, and it's about to grab on. And the idea is you capture it, and then you tow it down to a low enough orbit. Oops, sorry. You tow it down to a low enough orbit that the atmospheric drag will bring the satellite down and incinerate it, essentially. It's quite difficult for a satellite to actually get through the atmosphere and present any threat afterwards. Most of them will incinerate into tiny pieces, or dust, essentially. Very occasionally, and depending on their geometry and drag, one may get through, but it's not really worth worrying about. Okay. So my supervisor, Dr. Steve Ulrich, he actually performed experiments with the same control algorithm that I did, called Simple Adaptive Control, or SAC. He used this at the Spheres facility, and basically he had when you're doing these tests physically on Earth, experimental setup, which is basically a large, super smooth table. And you have robotic platforms like you can see right here that actually have, they're essentially miniature hovercraft that float on top of this table, which provides almost no friction. So you basically get frictionless movement, at least in a planar environment in the X and Y directions. And obviously you can't get frictionless movement in 3 dimensions on Earth because of gravity, but this technique works quite well for testing out planar orbital maneuvers. My supervisor's experiment was more limited than mine. He only tested this adaptive control algorithm in a straight line. And so what my research did was it did a more robust experiment. It varied mass and perturbations more, and it also tested out a circular trajectory. And the importance of that is that you want to circle a piece of junk and survey it before grabbing it. Often you would do this to actually generate a 3D model of what the cleanup satellite is looking at, so that it knows where to grab on with its robotic arm or whatever capture method it happens to be using. And in some cases, the piece of debris that you're looking at may have changed from its original design. So you could look at the blueprints that were used to build the satellite before it was launched, but if it was damaged, for example, you might have to adapt to that. So it's much better to actually circle the debris and get a real-time 3D model of it in case it changed geometry. So before this experiment could be performed, we actually had to build the facility because there was essentially nothing in the lab when I started. It was kind of exciting because it wasn't like walking into a well-established lab and simply performing an experiment, but I got a lot of an opportunity to build the lab itself. I was mostly in charge of developing the ground station computer that you can see here, and programming sort of the brain of these 2 platforms, which represent satellites. Generally speaking, the red platform was used to represent the cleanup satellite, and the black platform is used to represent the debris. So I won't go into too much detail on this, but there was a software environment developed that included several devices and platforms. Basically, you would first program a simulation on the computer using MATLAB and Simulink. If the results were good, then you would move on to an experimental test. And basically the exact same code that was used for the simulation could be put right onto the platforms and then used for the experiment. This is a little closer look at the platforms. So they're about 30 centimeters cubed. They're comparable in size to like very small, like microsatellites and CubeSats. They weighed 17 kilograms. They had 3 air bearings. You can sort of see the little blue pucks. There's 3 of those on the bottom, and then there's an air tank sort of sticking out of the side. They had 8 thrusters to control movement, and they were powered by a Raspberry Pi 3 computer. And then in order to experimentally validate results, we had LEDs on top of the platforms, and then we had cameras set up looking down from the ceiling of the lab to track their true position. And this is sort of a top-down view of the experimental setup. So there's that very smooth table I was talking about. The debris platform is in the middle, and the chaser or the cleanup satellite is just off to the side. And then this represents a circular trajectory around the debris. And in order to simulate perturbations, we basically used a very strong fan that was placed a little away from the table right here. And that sort of simulated a fairly significant external force trying to push the satellite off course as it was trying to complete this mission. And in order to get an idea of how well the adaptive controller is performing, we were comparing it against a proportional derivative controller. So that was basically our control. So right, there's a top-down view of the platforms. And I believe there's a video coming up. Yeah, well, first there was a simulation. Oops, sorry. And so this was a simulation under the simpler conditions where the fan is not, or the perturbation device is not pushing on the platform. And as you can see, sorry about that. The debris is tumbling, it's spinning out of control. That actually makes it difficult to capture, but that was beyond the scope of what I was doing. I was more concerned with how to control it after capture. And we're doing a circular trajectory around this piece of space junk to basically understand its geometry so we know how to grab onto it. And then here's an actual experiment that's being performed. And so this is sped up actually about 10 times. So this experiment was approximately 3 minutes long. And this was under the nominal conditions where it was not being disturbed by a perturbation device. I'll talk a little bit about the results from the nominal case, and then I'll show how the adaptive controller kind of has to struggle to handle the fact that it's being pushed off course. Okay. Right, so under the nominal conditions, the results were virtually identical, which they should be, because if you want to compare an adaptive controller to another controller, then under nominal conditions, you want them to be basically the same performance. Then you add the more difficult conditions and you see how each one performs after that. I actually had a little bit of trouble getting them to perform exactly the same. In the nominal case, the adaptive controller actually performed slightly worse. But that was fine because my thinking was basically, if the adaptive controller is tuned for worse performance in the proportional controller in the nominal conditions, then if it's still able to perform better afterwards, that's even more impressive. And here's an example of the adaptive controller performing better than the regular proportional derivative controller. So on the y-axis of the graph, we have tracking error. So essentially, how far off the circle is the cleanup satellite from where it should be, and then the duration of the experiment. And you can see that the adaptive controller it's slowly decreasing its tracking error. And that's generally speaking what it's adapting to the conditions, whereas the proportional derivative controller, it's basically cycling up and down, and the tracking error never really stabilizes. And especially from this period from about 60 seconds to 120, you can see the proportional derivative controller had much worse tracking error, while the adaptive controller was able to basically stay within 4 millimeters. Okay. So this graph might be more visually descriptive. Here you can see on the left, we have the proportional controller, and on the right, we have the adaptive controller. And on the left, you can see this gray area around the line is essentially 3 standard deviations representing the worst results that it had. So it could not follow the line consistently. This was actually I think 5 trials that were performed, and you can see with the with the adaptive controller, even with 5 trials, the spread of the data was very tightly. It was close to the line, whereas the proportional derivative controller, it was veering off course far more. And that's basically just another representation of the same data. That's probably a bit too technical to get into. That's talking about the adaptive gains inside the adaptive controller. One other thing that was interesting to look at was a piece of space debris might have unknown mass, and you might also be subject to external forces disturbing you while you're trying to capture it. But which effect is worse, or which effect would have the greater impact on performance? And so I actually tested both separately, and it turns out that at least as far as this adaptive controller is concerned, the perturbations had a much greater impact than changing the mass. So what we actually did was we did a test where we doubled the mass of the platforms. We put heavy weights on top of them and literally doubled the mass. And the adaptive controller handled it perfectly. And the proportional derivative controller didn't have too bad of a time with that either. But it was the worst was when you did both. If you both changed the mass to something that the system didn't know and introduced perturbation forces, that's when you had the worst performance. But as you can see on the right, the red part of the graph is for adaptive and the gray part is for proportional derivative. The error was still much smaller for the adaptive controller. Yeah, that's basically it. I could have gone into a lot more technical detail, but I didn't want to bore anyone. So are there any questions?
Okay, folks, if you have any questions, please feel free to type them in the question and answer field.
Oh, I guess I should.
Oh, there we go. Can space debris kill astronauts?
Most definitely. I believe that in orbit, it all depends on your relative velocity, but there are pieces of debris that are going around 7 kilometers per second, which I if I'm not mistaken, is roughly 10 times faster than a bullet. So yes, definitely.
Okay, let me see. What will the effect of the SpaceX launching thousands of satellites do to the accumulation of space junk?
That's a really good question. And I actually looked this up, and I was really impressed to see that he has a deorbiting plan for all of the satellites. It's actually described right on the website. I hope this becomes sort of standard procedure or policy going forward for people launching things, because there is already a lot of junk. And as long as you know the approximate lifespan of your satellite and you reserve enough fuel at the end of your budget to go down to about 600 kilometers is the sweet spot. If I go back to that graph where it showed what if we do nothing, you can see that that's basically where atmospheric drag becomes very significant and it pulls you down very fast. Let's see. Slide. Yeah, so you can see right around 600 kilometers is a sweet spot. If you can get that low, the atmospheric drag kind of takes care of the rest. But if you can't get down to 600, you'll be up there for quite a long time. Centuries, basically.
Next question is, what are the risks to the cleanup tug?
That's a good question. Oh, I should have mentioned, actually, the cleanup satellite is basically on a suicide mission because it has to burn itself up as well at the end. Otherwise, you've removed one piece and added another, so you've effectively done nothing. So, but in terms of risks, maybe during the mission, one of the scariest parts of the whole cleanup mission is actually, I can maybe show in that this video, the first one. This is the scariest part of the whole cleanup process, when your robotic arm is about to grab on, because usually the space debris is tumbling about its central axis, and it can be tumbling quite quickly. And if it could basically rip the robotic arm off if you grab on and it's rotating faster than you are, or you haven't matched its motion. Actually, that was another very good reason why you need to be able to perform a circular trajectory on a piece of debris. You basically want to match its angular velocity so that there's no relative angular velocity between you and the debris. That way your arm can grab it without being ripped off, basically.
Okay, another one was, were the perturbations affecting both objects?
Yes, they were. We weren't terribly actually, that's a very good point. That has more to do with capture as well, because the perturbation could be moving what you're trying to grab. So it's moving you and it's moving what you're trying to grab. Uh, because we didn't actually perform a capture in this experiment, we didn't really get any data for that. But I could definitely imagine that in a real scenario, yes, your target could be moving around a little bit due to perturbations. You definitely have to take those into account when you're approaching it to grab it.
Okay, so there's a sort of related question here. What might cause the perturbations in a real satellite situation?
So the dominant one is definitely the fact that the Earth is not a perfect sphere, and it's sort of slightly flattened shape means that as you pass over it, you're actually the effect of gravity that you're feeling is changing a tiny bit. I believe this is usually called the J2 perturbation effect, and that's by far the most significant one that you'll experience. But there are others. One of the things that makes this really difficult is that unlike ground vehicles or even aircraft, you don't have the benefit of friction dampening out tiny forces. So if there's anything happening over a long time span, even very, very small things, like for example, solar radiation pressure, literally just photons from the sun pinging against the side of a spacecraft. If it happens for long enough and there's no friction to oppose it because you're basically in a vacuum, it can generate enough force to send you significantly off course.
Okay, so next question, there's two questions from this person. What are the next steps in your research, and what limitations in control for the size of the debris?
The next steps in the research, I'm hoping to launch a career in the space industry, so I'm not sure. It's sort of an exciting question, but we'll see where that goes. But in terms of what the lab is doing, because I basically helped build the lab as well as before I could do my experiment. So the Spacecraft Robotics and Control Laboratory at Carleton, or the SRCL, I believe they actually want to do some tests with our table actually grabbing debris. So if I can just quickly go back to show a top-down view of the table. Oops. Right, so I had one colleague, Alex Crane, who was actually working on a robotic arm, and I believe he may be, or at least his work would be the basis for actually grabbing onto the target in the middle and then getting actual data about, depending on how quickly the debris is spinning, how much force will it put on your arm? At what point would it threaten the integrity of the arm? Yeah, that's definitely an important next step.
Okay. Is there a concept whereby a deorbit vehicle can process more than one piece of space debris?
Yes, actually, that's a good question, because in my undergraduate degree, also at Carleton in aerospace engineering, for my final year project, I was actually working on a very unorthodox method, where you basically grab onto the debris with a robotic arm, and you start spinning, and you continue to spin faster and faster, and then once the debris is facing towards the Earth and your cleanup satellite is facing a higher altitude, you let go and you basically throw the debris down, so it burns up, and then you actually get launched higher up so you can grab another piece, and then you basically repeat the process. You can do that until your fuel budget runs out. That's really the limiting factor, is how much fuel do you have? Because if you run out of fuel, and you haven't completed your mission, or you haven't deorbited yourself, you've actually made the problem worse, because now your cleanup satellite has become a piece of junk up there.
Okay. Is there going to be a division within each country's space program to develop in the future for projects specifically regarding cleanup on the debris?
That's a really good question. I know that the European Space Agency, I believe, recently put out I'm trying to remember this exactly. No, I don't want to give incorrect information. The memory's too fuzzy, so I don't want to say it. But definitely all space agencies going forward should be thinking about, are the satellites that I'm putting up there going to come back down, or am I just polluting? Like, I know there was a mentality early on, especially during the Cold War, and when we sort of were first launching things into space, that you don't need to worry about it. We'll never pollute space. I think the idea of polluting an orbit wasn't even in the human imagination at that point. Now it definitely is. But in terms of each country doing it, I fear that there might be a sort of tendency to wait for the next guy to do it. It's sort of a very diffuse problem that affects everyone, and so I think there's a tendency to sort of hope that someone else does it, but I hope that mentality changes.
Okay, just we've got a few more questions here. We're going to have to cut it off. What range of angular velocity should we expect from an average piece of space junk?
Angular velocities is a good question. That does relate more to capture. Actually, I had a colleague in the lab who's about to complete his PhD, so soon to be Dr. Kirk Hobble. He actually innovated a method to capture debris using a tether, and he would know a lot more about angular momentum than me. I don't have the numbers offhand, but I do know that if you use a tether that actually forks before attaching, and it's essentially like a single line going from the cleanup satellite that splits right about here and connects to both sides, that Y shape helps dampen out the angular momentum. So I can't tell you how much it is, but I know that tether strategy dampens it out effectively.
Okay. Somebody said all that is needed to remove some energy to cause a satellite to degrade orbit. So wouldn't a magnetic pulse be better than a physical connection with a tug?
That's a really good idea. Yes, I think that could work. I remember actually hearing one idea about removing trace amounts of material from edges of satellites using a laser, just to cause tiny little shifts in its momentum, and to change its center of mass to cause tiny shifts. And you could somehow use that to bring it down. Yeah, that's a very interesting idea, using a magnetic field. I guess the question would be how would you project it, but
and also how much ferrous materials in the satellite as well would
yes,
have an impact
that's
on
true.
that. Yes,
some would be better suited for that than others, I guess.
Yeah. Okay, second last question: how would satellites containing nuclear material be disposed?
That's a really good question. I guess they're talking about the sorry, I'm blanking on the name. They often have a radioactive energy source. I don't know. I don't know if I'd want that to re-enter the atmosphere and spread out. I mean, if it did re-enter and burn up and turn into dust at fairly high altitude and spread out, I imagine it would be so diluted that it wouldn't be noticeable. That would be my best guess, but I'm not sure.
But trying to sell that to the populace, we're deactivating a radioactive satellite, but don't worry about it.
Yeah, it's a good point. You definitely want to do some calculations on that.
Absolutely. So last question here. How autonomous might these cleanup missions be? Would all the decisions be taken in orbit by the cleanup tug? And how much human decision making per mission?
That's another good question. I would imagine, especially in the beginning, because I believe this type of mission hasn't been done before. They want to do it, but it's being theorized. You would definitely want it to be very manually controlled and have a lot of human oversight. Once you had done it successfully a couple of times and had a method that you were confident in, that's when I believe you might be able to automate it more. Certainly, obviously, the cleanup satellite is autonomous and does not have anyone on board because it has to burn up when it comes down too. Unless there was some way to refuel it in orbit, or Elon Musk comes up with some crazy way to bring it back down safely and have it land and refuel it and send it back up. But
okay, well that's great. Thank you very much for your presentation. That's quite fascinating. And good luck in your career in the space industry as well.
Thank you.
If anybody here has some positions, I know Dave would be interested.
Would you like, would it be appropriate for me to, I have a link to my thesis in case anyone's interested in reading more. It's in my resume. If you want, I could drop that in the comments or.
That was actually sent out to everybody as
Oh,
in the
it
invite to
was.
the meeting, so that everybody's got that.
Oh, thank you.
Okay. So, and your email will be in the thesis as well, right?
Yeah, yeah.
Okay, super. Well, thank you very much. And okay, so Chris, if you can bring up the rest of the slides, you're welcome to hang around, Dave, and see the rest of the observations and stuff as well. I'll just there we go. So we're going to take a 5-minute break, and we have the standard Messier and Moon challenge. So if we move to the next screen here. There, you've got 5 minutes to figure out what these two things are, and we'll give you an answer after the 5-minute break. Okay, so we'll see you then. Okay, folks, we're coming up to the end of our 5-minute break. So Chris, if you could move on to the next slide, please. Okay, so the Messier was the Black Eye Galaxy and Copernicus for the moon object. So Sharon, are you ready to go there?
Hi, can you hear me?
Yeah, we can hear you. No problem. We can't see you, but that's fine.
Yeah, there's no camera.
Okay, not a problem.
So good evening, everyone. Just a brief update on what is going on with the Dominion Observatory Preservation Committee. While members in our committee are still working on designating the Dominion Observatory with further National Historic Site status, I have been writing further on the history of the past staff who worked there in that observatory, particularly the women astronomers who worked under the observatory with the telescope, the main telescope, and that would be Mary Gray and Miriam Burland. One of my journal articles can now be read online at the website for the Society for the Study of Architecture in Canada, SSAC. Is it possible to switch the slide,
Yep,
Chris?
Yep, there we go.
So you can see it there over to the left. And I'm also going to be publishing another article soon. It should be up online this following week. And that would be on the Ingenium channel, which you can see down in the bottom center. And the article there on Miriam Burland, and then the image at the very far right is Mary Gray. So that's in reference to the Women in Science Day for STEM, which happens on the 11th of February. And the article that will be online will be labeled Celebrating the Notable Women Astronomers. And so I've written more on that in relation to the Dominion Observatory. So if you are looking for something to read online in the next week or so, you can check this out on the history of our women astronomers in Canada and the past ones that were related to the Dominion Observatory. Thank you very much.
Okay, thanks, Sharon. If it's possible, if you could maybe just capture these links and send them out to the RASC group, so we've got it, and we'll try to get into Astronauts as well.
Okay, will do.
Okay, super. Thank you very much. Okay, we're going to move on to our observation reports, and we've got Rick Wagner is our first person here. Let me just turn off the spotlight off of me. And where is Rick? There he is. He's coming out of the moon. There we go.
All right, so I think I'll just let you sit and look at that for a minute and figure out what it is. Over the past few years now, I've been trying to reach 150 observation sessions in a year. And this is the third year in a row now that I haven't made it. I came up this year with 146, which I thought was disappointingly close. I took 9,000 CCD images and another 4,200 frames with my DSLR. So my disappointment in not getting to 150 is somewhat mitigated by the fact that I'm the lead of the science team for the RASC remote telescope. So we were able to get 50 nights of observing in California and shot 4,900 images. So we got a lot of observing done last year. So one of the last things that happened last year was the conjunction of Jupiter and Saturn. And it was a lovely sunny day on Friday, 2 days ahead of the closest approach. And I realized that the weather forecast was really poor for the coming few days and that I'd better try and get out and see it now before it started getting worse. So unfortunately, my horizons are all covered in trees. So I wasn't going to be able to see it through the Boltwood 16-inch scope after dark. So I decided to try a daytime view. And this is actually the view through my 8.8 millimeter eyepiece, 240 power. And what I found was I could find Jupiter with just the eyepiece, but I could not see Saturn. So I put in a deep red filter, and that increased the contrast, and Saturn was barely visible. It probably doesn't show here, but the Saturn, you could actually distinguish the rings quite nicely, separate from the disk. And you could even see the shadow of the disk on the rings. But that was about the limit. And then Jupiter, the equatorial belts were absolutely solid, easy to see. Temperate belts popped in and out a bit. And at one point I thought I was seeing hints of possibly the Great Red Spot down in the southern hemisphere. Next, please. So later that evening, in fact, we had a science run with the remote telescope. And so after having set everything up, got the camera cooled, I'm waiting for nautical twilight so I can start imaging. And I just popped the telescope over to Jupiter and Saturn. So this is about another 6 or 8 hours closer to closest approach. Jupiter is way too bright to shoot with the 16-inch. So what I did was I shot through their sulfur 2 narrowband filter, which enormously dims the image. And then I was able to get Jupiter with 3 of its moons, and then the Saturn is kind of burnt into just the oval from its rings. Next, please. So the closest approach was on Monday and Tuesday, and it was indeed cloudy. However, Tuesday afternoon, it was possibly going to clear up in time to see something just after sunset. So Jeanette and I found ourselves in Kingston going for groceries. So I brought along my camera on the tripod, 15 by 70 binoculars, and an 8-inch Dobsonian telescope, the normal things you take to the grocery store. And about 4 or 5 o'clock in the afternoon, it cleared off perfectly. And we headed up to Old Fort Henry, to the parking lot there to take a look. And as twilight progressed, we did eventually find them. This is roughly the view sketched after the fact, the view through my 8-inch Dob at 130 power. And you can see 4 of the Galilean moons again. There was actually about 24 people, or rather, sorry, 24 cars of people up in the parking lot at Fort Henry to see the conjunction. So I also looked through the 15 by 70 binoculars. You could see Jupiter, the oval shape of Saturn, and the 4 Galilean moons. So then started to take pictures with the camera. So next. So this is a view of the 2 of them. You can see the bright one, Jupiter, quite easily, and Saturn is just a hair to its right. So this is looking over the top of Fort Henry. I thought it was interesting taking a picture of a cannon with my Canon. Next. This is the shot I was really up there to get. So you can see Jupiter and Saturn on the left, the lovely deep colors of twilight, and then the city of Kingston in the foreground. Next. So one of the, getting back to the RASC remote telescope, one of the things I've often been interested in observing, and I've never actually followed up on it, there's a star called 40 Eridani, also known as Omicron 2 Eridani. Some of you will recognize, I think this is the star that Spock's planet Vulcan was supposedly orbiting around. Don't quote me and don't correct me if I'm wrong, because I don't. But anyway, so the bright star here is 40 Eridani. And you can see right next to it is a little pair of stars very close together, one rather bluish and one rather reddish. And the blue one of the pair is what's really interesting in this little scenario, because it's a white dwarf star. White dwarfs are generally very, very faint. This one is something like a 300th as bright as the sun. And so unless they're very close, you can't see them. And the only other two close ones that I know of are sitting right in the armpit of Sirius and of Procyon, one of the other brightest stars in the sky. So unless you're very lucky or probably have very good equipment and very good conditions, you're not going to see them. So this is one that's quite easy to see. It's about 83 arc seconds from the primary star. And then the little dimmer reddish star is also quite interesting because it's actually a red dwarf. And we don't get to see very many of those in the sky either, in spite of the fact that there are, millions of them out there. This one is somewhere down below 1,000th of the brightness of the sun. So go out and check them out. Easily be able to see the white dwarf with probably a 4-inch telescope. You might need a 6-inch to pull in the red dwarf. The separation between the white dwarf and the red dwarf is 9 arc seconds. So it's still not difficult to split. So amongst the three stars, it's quite interesting that the little dim white dwarf actually would have started off as the largest and the brightest of the three stars. It's also the heaviest, which means it burns through its fuel a lot more quickly, turns into a red giant, blows off much of its outer mass, and then contracts down to become the very dim and very small white dwarf. The main star, the primary brightest one, will follow that route probably in something like, a billion to a few billion years. It'll follow the same route. And then the red dwarf, because it's so light and it burns its fuel so slowly, it'll probably go on another 10, 20, 30 billion years before it starts to do anything very exciting. Next, please. So the other thing we have mounted on the remote telescope is a Canon 6D full-frame DSLR that's been modified for improved H alpha and 200 millimeter f2.8 lens. And it's just mounted piggyback on the scope. And I was doing an hour of exposures on one of the Cepheids, well, in fact, 3 of the Cepheids in Messier 31. So the telescope's pointed there anyway. I thought I would grab an hour of images with the Canon. So it's about a 10 degree by 6.5 degree field of view. Beautiful, does a lovely job. So, and I think that's all I've got. Thanks.
Thank you very much, Rick. Jim, Sophia, you're up next.
Thank you. Hello, everybody. So this snapshot image of the Rosette Nebula is what I saw on my computer screen about 90 seconds after 90 seconds of exposure and live stacking using the Mellencamp Skyraider video camera and the William Optics 80 millimeter refractor. It was a cold night and a waning gibbous moon, but remote inside viewing off the balcony and a good light pollution filter helped with that. The filter that I used was the Idaeus NBX Nebula Booster. Next one, please. And this is the same image of the Rosette Nebula after post-processing using Topaz Studio. Next one, please. This image of the Jellyfish Nebula was taken the same night after 2.5 minutes of exposure and live stacking using the same equipment. Next one, please. And this is the same image after post-processing. You can see the head of the jellyfish on top and faintly some tentacles below. This is a new one for me. The Jellyfish Nebula, known as IC 443 in Gemini, is 5,000 light years from Earth. It's a supernova remnant interacting with surrounding molecular clouds, which makes it quite huge. It has an angular diameter of 50 arc minutes. The full moon is 30 arc minutes for comparison. It looks like I'm going to visit this one again, and I'm hoping to capture more of the trailing tentacles of the jellyfish that I've seen in other images from our members. Thank you.
Thank you, Jim. Andrea, you are up next.
Okay, I also took pictures of the Jellyfish Nebula. This image was taken with a William Optics Red Cat 51mm aperture telescope. And as Jim mentioned, it's an extremely large supernova remnant in Gemini. And this is about an hour's worth of exposure time. I did use the L Extreme filter, which will filter primarily for hydrogen and oxygen. Next image, please. The next, oh, okay. This one and the next images were all taken with the Hyperstar lens on my Celestron C11 Schmidt-Cassegrain. The Hyperstar turns the very narrow field of the Schmidt-Cassegrain into a very wide field telescope. So this is about really interesting. What is the that one up? This basically
You're really breaking up there, Andrea.
it's a huge curve.
Dave, it's Chris interjecting. Maybe you can turn off her video or her spotlighting.
Yeah, hang on a second here.
I'm gone. Am I back?
You're back. Okay.
All right. We'll just go quickly that this is a very nice nebula in Perseus. It has lots of dark clouds and dust lanes, and it's a star forming region. It's very pretty. Next image. This is M74. It is a galaxy. It is in Pisces, and it is very far south, just below Mars at the moment. It is extremely large, a face-on spiral galaxy, and very beautiful. And it is about 10th magnitude and 32 million light years away. I took this as well with the Hyperstar. The next slide, please. These two galaxies need no introduction. That is M82 and M81 in the constellation of Ursa Major. They are very bright visually, and they are very bright in the telescope. Between the two galaxies, there is something called the Interflux Nebula, which sounds kind of crazy, but basically there's a little smudge above the Bode's galaxy, the spiral, and it was a smudge, and I couldn't figure out what it was. And I looked in other images and I saw this smudge. So it looks like that was the beginnings of trying to image the Interflux Nebula, which is something that I'll have to take more time on this image to process and to locate. I apologize for the poor connection. That's it.
Okay, thank you very much. So we have a new contributor tonight, Jamie. So maybe you can introduce yourself, Jamie, and let me just spotlight you. There you go.
Hi. I'm down here in California in the Santa Cruz Mountains. I take most of my photos from the backyard, but I live in the redwoods, so I really have to plan because there's a few gaps between them. So, but I managed to get some shots though, right? But I really have to wait for them things to show up in the gaps sometimes. Let's see, my claim to fame, I guess, is that a long time ago, I worked on the space station when I lived in Vancouver. So that's my claim to fame. That's probably the most exciting thing I've ever done. Now I work on boring stuff. So that's a little bit about me. And this shot is the Rosette Nebula. And I also have a hyperstar. I'm new to the hyperstar though. I got it a couple of months ago. And I use it on a Edge HD 8. So this object has a lot of numbers. When I was looking it up, it had these NGC numbers. There's 2237, 2238, 39, 2244, 2246. I'm really not sure why it has so many numbers, but it's got a lot of them. I guess there's lots of objects within it. I see this is a narrowband image, so it's hydrogen alpha, roughly 30 shots at, I think, 180 seconds each of each narrowband, using the Hubble palette. So oxygen 3, hydrogen alpha, and sulfur 2. So it has several O-type stars, which are very bright and hot, and those light up the neighborhood gas and dust, making it very red with the H-alpha light. But when I process it, of course, it's narrowband, so you can play with the colors to try and bring out the different aspects. And I played with the colors on this, and that's why it has kind of a different color in the middle. I didn't get this rainbow effect, apparently. Some people try and go for it to get the middle blue, but I kind of tried that, and it didn't look very, I think I lost some of the information in it when I did that. So I stuck with this. And yeah, so that's it. So next slide. This one I'm really happy with. This is very cool to me. I got very lucky. I had no idea that a comet happened to be passing through the area when I took this photo. And the comet, which I expect is very bluish, was at this position happened to be at this position on the night that I was shooting oxygen, which gives the bluish colors. So I totally lucked out on this one. And I took a double take at the fuzzy blob in the photo when I was first looking at the images coming through. And I looked it up quickly and I thought, oh, that must just be one of those stars, one of those bright stars. But a few days later, I thought about it some more, and I plugged it into Sky Safari, which I used to do my planning. And I saw, yeah, there was a comet passing through that same night I was photographing. So I thought that was really cool.
Which comet was it?
The Atlas comets.
Okay.
This is IC 410, of course. Sorry. It's called the Tadpole Nebula. And if you look closely, you do see the two tadpoles. I don't know if I was able to bring them out in my photo, but I could see them. They're estimated to be about 10 light years long, and they're possible sites of ongoing star formations. And I think that's about it for me.
Okay, thank you very much, Jamie. So we're going to turn it over to Bob Olson. There we go, Bob, you're live.
Okay. This is the Beehive. It's a fabulous, nice bino object for binoculars. It's about 600 light years away. And interestingly enough, it's one of the first objects that Galileo pointed his telescope at. Next image, please. This is the Pleiades. It is at 444 light years away. It's the closest of the Messier objects to Earth. Easy naked eye and a wonderful binocular target. I'm not sure you could see the nebulosity with binoculars though. Next image, please. This is one of the challenge objects, and it's a dwarf galaxy, very hard to see, very faint. This is an 8-hour exposure. It was discovered in 1906, which tells you that it's not easy to spot. It's 2.4 million light years away, and it's part of the local galaxy group, which includes us, the Andromeda Galaxy, and M33. Next image, please. This is the Owl Nebula. 2,000 light years away, Planetary Nebula. It's easy to see why it's called the Owl. The guy who first saw it made a drawing of it, which you would swear was an owl. I'm thinking he maybe saw an owl out his window and made a copy of it. Next image, please. This is the Eskimo Nebula. It's got a pale blue face inside of a green parka hood, which is where the name comes from. It's actually looks more like that in mono than it does in color. It's another planetary nebula. It's about 6,500 light years away. And I blew this up like you wouldn't believe. It's this a little tiny part of my image. As you can tell from the bloated stars, it's pretty small. Next image, please. Another one of our challenge objects. It's a galaxy, an edge-on galaxy, actually circles around in orbit with M77. They orbit each other, I guess you'd really say. It's about 55 million light years away. Pretty nice edge-on. The two bright stars might make it easy to find, but hard to see using a telescope. Next image. This is one of the frames that I used when I was imaging this. It's a 10-minute exposure, and I get satellite tracks all the time. But this one's just a little bit unusual, you know, the two parallel lines. And show me the next image, please. These parts, including the tracks, appeared only on this frame. All the other images did not have these in it. And so a little bit unusual, the bright lights being right on the tracks. Typically the track doesn't have a bright light on it. The center one with the two little comedy looking things around it, kind of unusual. I showed this to Ginny, and she said that it was obviously a UFO taking off from Roswell. And I actually sent it to a conspiracy freak friend of mine in British Columbia. I thought I'd be interested in what he had to say. And he said it was the best evidence he'd seen that the election was stolen in the USA. My response to that was, yes, it is the best evidence you have. He didn't get the joke at all. Now, in truth, it's about the right size for an airplane flying through the image. So my guess is those are the wingtip lights. that flash every once in a while. So you see the flash. And the middle one is a flashing light on the fuselage, probably lighting up some part of the airplane to make the two comet parts. Wild guess, no idea really. Next image. Well, we've seen lots of the jellyfish tonight. As has been said, it's a part of a supernova remnant. I showed, when I look at this, it looks exactly like a jellyfish. I can see it floating in the water and the tentacles hanging down. Ginny looked at it and said it looks exactly like a brain. Thank you very much. Have a good night.
Okay, thank you, Bob. Jim Thompson is up next.
All right, good evening, everyone. You can hear me all right, Dave?
Yep, no problem.
So January was a pretty good month for observing from my perspective. I was able to get out for 3 solid observing sessions, along with a 4th night of rapid lunar observing before clouds rolled in. My images tonight begin with the Lunar Observing Challenge for January, which is Mare Cognitum. You can see it here in this image that I captured back in December of the full moon. The 350 kilometer diameter impact basin is close neighbors with Mare Nubium down in the lower right there in the inset image, and Oceanus Procellarum. It is marked with numerous bright ejecta rays over top of flood basalts of different vintages, as denoted by the different patchy color variations in the dark material. The striking lack of craters also gives away that the area is significantly younger than the brightly colored highlands that surround it. Next image, please. I've added some additional annotations to the image, indicating some interesting nearby craters as well as some interesting space mission landing sites. Or in the case of Ranger 7, crash site. That's where that probe landed at high velocity. Before we leave this image, take note of the bright ejecta rays radiating down from the top of the image. These are from crater Copernicus, which is about 500 kilometers to the north of the Mare. Next image, please. So these two images show how the area around Mare Cognitum looks under different lighting. The image on the left is from almost 3 years ago and shows how the area looks a day or two after the first quarter. The Ripheus Mountains really stand out nicely in this image on the left-hand side, as do the wrinkle ridges that zigzag across the floor of the Mare and down to the south. The image on the right is from around last quarter, or maybe a day or so past last quarter, and it was captured just this past summer. Interesting to note is that this area has been, at some point in the past, active with volcanoes, and I will quickly mark them here with the annotation. So this area here, you can kind of see it better here. It's kind of uplifted, so that's a volcanic dome. The area around this crater is also believed to be a volcanic dome. This bump right here. And then there's a couple of small ones down here that are really hard to see, but they are there. So those are all considered to be, at one time, active volcanoes, which is kind of interesting. I kind of like to hunt for volcanoes as one of my areas of interest looking at the moon. By the way, both of these images were captured essentially the same way. They're both captured with a 10-inch Ritchie-Chrétien scope and an ASI 183 monochrome camera using an infrared high pass filter. So just using the infrared light coming from the moon. They are stacks of the best 10% of 3,000 frames, stacked using AutoStacker 3 and wavelets applied in RegStack 6. Next image, please. My final image is from the first light of a new telescope I bought about a week ago. It's a bit more of a week, I guess. It's called a TPO Ultra Wide, and it's sold by Ocean Pacific Telescopes down in California. It is a tiny little triplet APO with an aperture of 40 millimeters and a focal length of 180 millimeters. So that gives a F ratio of 4.5. I put it on my ASI 294 camera to give this very wide field view of the Orion Nebula. This is a live stack of 30 20-second exposures with no post-processing other than some tweaks to the levels and some correction for vignetting, which was pretty minor. So far, I'm very happy with this little scope, and I hope to show you some more pictures from it in the future. Thank you.
Okay, thank you, Jim. We just want to quickly flip back to Jamie. There was a question that came up, and I didn't catch it while he was doing his presentation. And the question was, Jamie, do you expect the comet is bluish? Or do you perceive the color difference between the comet and the nebula?
Yeah, I believe the comet is bluish. Just by chance, a colleague of mine, I was posting it to, was sharing a link from the NASA, I think the 12 days of Christmas photos or something, and they had a really close-up view showing the pieces inside of the comet. And I think it was bluish greenish. I think that they usually are bluish greenish in color. And actually, if you look really closely at that comet image, you'll see two kind of bright streaks. And my guess as to what those are maybe the two individual pieces that were moving over the time, over the time that I was taking photos of them, over, I think, 90 minutes. And if you look at the individual frames before I stacked them, you can see the bright spots. And I think there's two of them. Yeah.
Okay, thank you very much for answering that question there. Sorry, I didn't catch that until we have moved on. So we're going to move on to Paula Cleninger. Just give me a second while we reposition the slides. And I bring Paul up here.
Hi there, Dave. Is my audio good?
Your audio is good. You don't want video?
No, I'll conserve the bandwidth. I don't want to run into issues with it.
Okay, not a problem.
All right. Hi, everybody. Well, January continued the rather dismal trend of cloudy skies we've had this winter, with only a few exceptions. And the few clear nights there were usually sported a pretty bright moon in the sky. So deep sky observing and imaging have definitely been taking a bit of a hit, at least out in my neck of the woods in the Lanark Highlands. So full disclosure, this image of last month's challenge object, the Pleiades, also known as the Seven Sisters, was taken well before our last meeting. This is an easy object to observe with a naked eye up in Taurus, and as Bob pointed out, it's especially beautiful through a pair of binoculars. This is the second closest open star cluster to us here on Earth after the Hyades, and is at a distance of about 440 light years. It contains many hot young blue O-type stars and is estimated to be about 100 million years old. On a clear night with normal eyesight, you should be able to make out 7 of the brightest stars. Under a dark and steady sky, those with acute vision may be able to resolve up to 14 members. And with binoculars, you can easily see dozens. With imaging, you can see many, many more. In fact, over 1,000 members have been statistically confirmed in this cluster. The blue reflection nebulosity around the brightest stars was once thought to be material left over from their formation. However, contemporary studies indicate that it's an unrelated dust cloud, which the star cluster is just currently passing through. Calculations indicate that the star cluster will disperse over the next 250 million years or so, which interestingly corresponds to only about one revolution around our galaxy. Next one, please. Well, this is certainly a more typical view of the sky that I've had in the last month. This was the moon trying to poke out between the clouds a few nights ago. The cloud density and the air temperature made for a halo of colorful iridescence, so I thought it was worth a quick shot. Interesting to see anyway. Next one, please. But as I mentioned, there were some nights of clarity with the moon up, and so I had a few opportunities for a bit of lunar exploration this month. Last month's challenge object, as Jim pointed out, was Mare Cognitum, and is indicated here. So we can zoom in for a bit of a closer look. Next one, please. There it is indicated there. This feature is a mare, or a lunar sea. It's essentially a large flat expanse of frozen lava, about 350 kilometers across. You can see that it's fairly devoid of any large craters, unlike regions in the moon's southern highlands. This indicates that the area became flooded with lava long after the early impact bombardment that peppered other older portions of the lunar surface. Samples returned from this area indicate an age of about 3.2 billion years, which is considerably younger than the moon's estimated age of about 4.6 billion years. Next one, please. So this is Mare Cognitum, also called the Known Sea. And it was actually only named that in 1964 after the successful mission of the Ranger 7 spacecraft. The area was previously considered to be part of Mare Nubium. Next one, please. Ranger 7 landed at the position indicated and returned the first ever close-up views of the moon's surface. It showed us that what otherwise looked like a really very smooth surface using even the largest telescopes on Earth was actually peppered with small craterlets down to the limits of the probe's resolution. In its final image before impact, it captured craters less than half a meter across. This was totally unknown at the time and extremely important to determine because the first Apollo moon landing was scheduled to happen only 5 years later. You kind of want to know what the surface looks like if you're going to try to touch down on it. Next one, please. So, given that the moon was available on a few nights this month, I was able to do some further investigation of something a number of us observed back in December while trying to view the Jupiter and Saturn conjunction. For those who missed last month's meeting, a quick recap here. On the night of December 17th, as the planets were converging, there was also a slender crescent moon in the sky that made for a nice photo op. I took this view with a 70mm lens to get a wide enough view to view them all. What struck me in this image, though, was a very bright spot of light near the moon's southern rim. At first, I thought it was a star undergoing a grazing occultation by the moon, but the point didn't change its position with respect to the moon in all the images I took that night, so it had to be a lunar feature. And thanks again to those folks who sent me copies of their images and observations after the last meeting. I really appreciate seeing such things from the perspective of other observers and of hearing their impressions of these observations. That certainly provides me with some ground truth on my own observations. Next one, please. So unfortunately, I only imaged the moon that night with a 70mm lens, so the resolution was limited, but still it revealed enough detail to help me pinpoint approximately where on the moon this light was coming from. What really struck me that night was just how bright this feature appeared, given that it was quite a distance from the southern tip of the lunar terminator. I've seen lunar mountains and craters on the dark side of the terminator similar to this before, but never quite so bright and so far removed from the terminator boundary. So I used the Virtual Moon Atlas 7 freeware program to compute precise details of the illumination angles, the lunar librations, phase, and so forth for the time and location of my observations. That's the data you see on to the right side there. This led me to believe that what I'd seen was actually one of the high peaks near the moon's south pole. So in these details of my image, note the last two items, the lunar librations. almost 6 degrees north in latitude and about 6 degrees east in longitude. For those not familiar with the concept of the moon's librations, these are measurements of the apparent wobble of the moon as seen from Earth as it moves in its orbit around us. Most of this is caused by the fact that the moon's orbit is somewhat elliptical and its axis of rotation is slightly tilted with respect to its orbital plane. As a result, we can at various times actually see a little bit over the top of the North Pole or over the bottom of the South Pole, and also a little further around the eastern or western limbs than we could see if there was no libration at all. So on this night, the almost 6 degrees in latitude libration meant that the moon's north polar region was tilted towards us, and therefore the south polar region was tilted away from us by the same amount. The eastern longitudinal libration meant that the right side of the disk was tilted towards us and the left side away from us. Next one, please. So in my investigation of this, I looked back at some previous images I took of the moon and found this one. This was taken about 3 years ago using the Opteka 500mm mirror lens. I remember at the time noting the 2 points of light at the southern rim of the image and thinking that they were either mountains or crater rims, but they were nowhere near as bright as the point of light observed in December. But notice the libration data for that night. The latitude libration was almost identical to that in December, meaning the north and south tilts were pretty much the same in both images. However, the libration in longitude was almost 7 degrees to the west that night, meaning there was about a 13-degree difference in east and west shift between the two views. And Chris, could I get you to flick back and forth between this slide and the previous one a few times? That'll make the effect of this libration pretty obvious. So you can see the features on the shift of the Mare features there, and as Chris flicks it back and forth. But significantly, you can really see the effect of the shift in the position of the bright knots near the South Pole. So this begs the question: are these the same lunar features being illuminated beyond the terminator? And if so, is the noticeable difference in brightness due to the amount of shift in longitudinal libration, or is it something else? There are a couple of factors that could contribute to the difference. First is the fact that the Opteka 500mm lens has a larger aperture and 7 times the focal length of the Canon 7mm lens that I was using in December, leading to a finer resolution of the detail. Also, there was a slight haze in the sky back on that night in December that may have increased the brightness of the feature. So definitely time for a closer look. Next one, please. So I was hoping to have another look for this feature in the middle of last month when the conditions of libration were similar to back in December, but unfortunately it was clouded over for us, or at least for me. Big surprise there. However, 12 nights ago, the sky did cooperate and allowed me to do some high-resolution imaging of the South Polar region. I flipped this image around so that south is at the top. This was obtained using my 11-inch Edge HD with an XImage 5 camera and a 2x Barlow lens for an effective focal length of about 5,600 millimeters. You can see that this is some pretty rugged terrain, and up along the rim, several mountains are apparent. As I mentioned last month, the location of the bright spot in the December view seemed to correspond to one of these mountain peaks, likely either the Leibniz Beta Massif or the Malapert Massif, 2 of the tallest mountains on the moon. So where are they here? Next one, please. So the first recorded observations of these mountains were made by the astronomer Johann Schröder in 1789, and he named them the Leibniz Peaks. He specifically identified 5 of them and labeled them alpha, beta, gamma, delta, and epsilon. He also made the first estimates of their heights and pegged them at around 5.5 kilometers, fairly substantial indeed. In my research, I came across this work by Edmund Neeson, published in 1876. This chart shows the same region as in my image, and you can see the peaks labeled here. I wanted to show you this chart because I have to say, it's given me a whole new appreciation for the work of these early astronomers. These folks didn't have the advantage of photography or computers or spacecraft views. and had to strictly rely on patient observation and sketching to record their findings. It's quite impressive, really, especially when you realize how tricky it is to make out details very close to the lunar rim. The foreshortening that occurs, coupled with librations and ever-changing shadows, can alter details substantially from night to night. Next one, please. A little bit of a sidebar here. If you're at all interested in reading some of this 145-year-old historical work, I found that Google has digitized Neeson's entire book and made it available as a free ebook download. You can grab a PDF copy of this by going on Google and searching the book's somewhat lengthy title, The Moon and Conditions and Configurations of its Surface. A number of links will come up if you do that, including some commercial reproductions that aren't free. Click on the one for books.google.ca and you'll get to the page containing the free ebook link. This is a really impressive body of work and incorporates the findings of other notable astronomers as well as such as Schroeder and Beer and Mädler. It spans actually hundreds of pages and contains all the original charts, descriptions, features, mathematical formulas, and numerous color illustrations of the prominent features, such as Plato that you can see up at the top. Again, this is well before photography was started to be used for doing lunar imaging or any kind of astronomical imaging. This is 145 years ago. Next one, please. So again, using the chart from the Neeson work, you can see the position of the Leibniz Mountains in my image as identified by Schroeder and documented on one of the Neeson lunar charts. I'd like to read you a short description of these mountains taken from his book. In it, he states that, quote, these are a magnificent range of immense mountains on the further hemisphere of the moon, visible in profile on the limb, extending from -60 to -80 degrees latitude, with a lofty crest fully 12,000 feet high and culminating in 3 tremendous peaks, Alpha, Beta, and Gamma, towering, according to Schroeder, over 26,000 feet above the level of the limb, a height that Beer and Mädler think is not overestimated, whilst many peaks range between 15,000 to 20,000 feet high, but are scarcely visible except under conditions of favorable libration. From their appearance, it's probable that these mountains consist either of a great highland like the Alps or extend in several approximately parallel chains like the Cordilleras. Wow, I find that even these estimates of the mountain's heights are impressive, given this was all done by measuring shadow heights and working with limited optics, no photography, and the vagaries of variable seeing conditions. Coincidentally, his chart and my image have pretty much the same amount of libration in latitude, meaning that the mountains poke up over the rim by a similar amount. While this was a lucky coincidence for me, the map was probably drawn this way on purpose by Neeson because this orientation, as it happens, has virtually no libration in latitude. In other words, the view has almost no tilt in either the north or south directions as seen from Earth. And this next slide shows what a difference that tilt will make. Next one, please, Chris. So the top view here is the same as the previous image. You can see from the data that the libration in latitude was less than 1/4 degrees from zero, so almost negligible. As I mentioned, this was taken 12 nights ago. The lower image was taken only 4 nights ago, and you can see that the amount of latitudinal libration has increased by over 6 degrees to the south, meaning that effectively we're now seeing over the top and even a bit behind the 2 indicated mountains. The difference in longitudinal libration between the 2 dates is only 1 degree, so not too apparent or significant. What I enjoy about these 2 views is that when you flip your gaze between the 2, you can get a much better sense for the 3-dimensionality of the terrain, especially near the polar mountains. So where does this leave us? Well, the image taken back in December had a latitudinal libration of almost 6 degrees to the north. That means compared to the top image here, it has as much of a tilt in the opposite direction as the bottom image has to the top image. That would place the mountains up and over the rim, leaving only their very peaks protruding above the rim. You can get an idea of why this gets a bit tricky to pin down which mountain actually caused the bright spot seen back in December. So next one again, please, Chris. So here again is the view from 12 days ago, showing the region from 80 degrees south latitude to the South Pole as seen from Earth, and a topographic view from directly over the South Pole, courtesy of the Lunar Reconnaissance Orbiter. I'm hoping to get a high resolution view like this when the libration conditions are similar to the view back in December. The next opportunity to do this is in the early evening of February the 14th. Perhaps then the specific mountain will shine again in the dark and make itself known. Next one, please. And considering February the 14th is Valentine's Day, perhaps you can take your better half out for a view through your binoculars or telescope and point out that this little blip of light at the bottom of the crescent moon is quite possibly where people from Earth will next set foot on that world again. Thanks for listening, and everybody stay safe. Take care.
Okay, thank you very much, Paul. So our last month challenge was M45, NGC 1055, IC 1613, and Mare Cognitum. We got some of the images from that, so thank you very much, folks. Moving on. Our Deep Sky Challenge, our beginner challenge this month is Messier 38. It's an open star cluster in Aruga. It's also known as NGC 1912. And 3,480 light years away. Intermediate challenge is Barnard 226. It's a dark nebula near Aruga, same area, near the open cluster M36. The advanced challenge is Siamese 147. It's a supernova remnant in Taurus, huge but a dim object. And supernova thought to have occurred some 99,000 years ago. Lunar challenge is crater Cleomedes, lunar impact crater, 126 kilometers in diameter, just north of Mare Crisis. And all these challenges will be in Astronauts, so you'll be able to get those shortly. Okay, there's a summary of what the challenges are. And Mr. Odell here is doing a session on Thursday, February the 11th on Impact Craters, a Discovery Adventure. It's an online event. And I believe it's from Facebook. Chris, is that correct?
Correct, yes.
Okay, so I guess you go to Facebook and look for Humanist Ottawa, and you'll be able to get the link to this particular session. Fred Lawson Observatory is still open, although under current COVID restrictions, limit of 5 people on the site outdoors. It's worked out pretty well so far. If you are planning on going, please email the group to say, hey, I'm heading out tonight from this time to this time. And that way we can control the numbers at the site. Unfortunately, our library is still closed. It's hidden inside the Aviation and Space Museum right now. Here are the folks that keep our club running. Thank you to them. And thank you. I believe your audience was up to about 120 people tonight. We'll sit down and analyze the numbers afterwards. Special thanks to David Rogers for his talk and all the folks who gave their observations. And thanks to Sharon for sharing the International Women's Day stuff that she's working on. And we're not meeting at Grace O'Malley's. In fact, Grace O'Malley's doesn't exist anymore. So we're going to have to find a new post-meeting entertainment location when we return to the museum. Membership benefits. For those who are not members, a regular membership is $88 a year. Family membership is $82.50 plus $15 an adult and then $8.10 per youth. And youth membership is $53. So what do you get with that membership? I'll go to the next screen here. So we have the Ted Bean Telescope Loan Library, if you are a member. Once the museum reopens, you'll have access to our library. We have our private observatory out near Almont, the Fred Lawson Observatory. You'll have access to that as well. And then nationally, you get the Sky News as part of your membership with RASC. That comes out every 2 months. The journal comes out every month. You can get it electronically by default, but you can add a little to your membership and also get a hard copy. The Amazing Observer's Handbook comes out sort of late December every year to all members. And then we have our Amazing Astronauts, which is our local publication. Gordon Webster looks after that. And he often has summaries of some of the talks here, as well as the observation challenges and many other interesting articles. Next meeting is Friday, March the 5th at 7:30 p.m. Any ideas for talks or observations, please email me, meetingchair@ottawa.rasc.ca. And thank you to folks who gave me some suggestions for upcoming speakers. I'm busy working away at that. And again, if you have anybody you'd like, maybe it could be yourself, don't hesitate to put your own hand up if you have something you wish to share with us. And we'll take it from there. So we'll see you on March the 5th, 2021 at 7:30 p.m. and stay safe. Thank you, folks.